Good evening. Thank you very much, Echo, for sharing that. I know that you and Carol and other people in our class? Khalid, great. Have been working on the container deposit law, so I hope to see change in Arkansas based on that. Today's class, if I had been more aware of my life and been more coordinated, I would have spent a little bit more time on this on Monday, considering that your pre-lab quiz was about this topic. Yeah, so sorry about that. So today we're going to be spending time digging into what you guys are doing in the lab this week, and making sure that you have a conceptual understanding, be able to calculate, and kind of piece everything together. So we're still talking about how fast the reactions occur. We're just talking about it now from a different angle. So I want you guys to take a look at this reaction. Can you decide or determine whether this is zero, first, or second order? Talk to your neighbors, see if you have enough information to figure that out. If not, what information would you want? This really doesn't work unless everyone does it, as you guys notice. So moving forward, if we can keep the momentum, I know we're almost halfway through the semester, but if you can keep the momentum and raise your hands as we're going through this, maybe we're a third of the way through the semester, third half, somewhere in that range. So can you guys easily answer this question, yes or no? Thumbs up, thumbs sideways, thumbs down. Yes, I can, no, I can't, maybe, or at least I can eliminate some. If you can eliminate some, put your thumb sideways. Okay, what more information might you want? Can I have some hands raised? I hear a lot of voices. Logan?
A plot of those points?
A plot of those points. Okay, great. What else might help in addition to that? Because that's a very good starting point.
I would like the concentration, the different molecules that are involved.
Okay, so I've simplified it and I basically said you have one reactant, this is your reactant. And so it's kind of like what we were looking at the other day, except instead of looking at multiple reactants, we're just looking at one. So what else? Did you guys do the pre-class quiz? What else did they give you that was useful in figuring out the order of reaction? What if we took that concentration versus time? These are the two pieces of data you have on your sheet, and that I just gave you. And then we do natural log of that value. If we punch that in our calculators, it gives us 4.605. Natural log is 71.4, that's 4.268. And then we try, what's 1 over that value? Let's calculate that as well. 1 over 100 is 0.01, 1/100, right? 1 over 71.4, 1 over 55.6. And so these two columns are calculated based off of this information here, the concentration. Can we answer this question now? Let's do what Logan asked. Let's actually plot, but let's plot all three of those. So we have our concentration versus time plot in the middle. We have our natural log of concentration, those values, we plotted that against the same time points. And we took all those 1 over concentration points and plotted them against time. What stands out? What stands out? Josh?
Straight lines.
Straight line. Where? Which one? Are all three straight lines?
No, sir. The third one. 1 over concentration.
Okay, only a graph of 1 over concentration versus time is linear. You will never see an example where all three of these are linear. So Lynn, what does that mean? Or do you have a question?
No, I just had 3 of the third one, sorry.
All right, so only one of these is linear, and that tells us something about the reaction. So what order is this reaction? Second order. Okay? If this was linear, neither of the other two would be. If it's only concentration versus time, what order would that be? Logan, how did you know that?
in the homework. So I mean, usually so it's like the formulas for like the equation that we're given in our lab as a handout. And so when it's like natural log times it, if that's linear, then that's going to be your first order. And then if it's like the concentration itself, if that's linear, then it's a zero. Because
Be a little bit careful, I'd say, concentration versus time plot, because concentration by itself isn't linear, right? There's no linearity to it. Josh?
Is that just experimental, like second order reactions generally? How do they come up with like straight line means?
There's a couple different ways of answering this. One is that physical chemists spend some time doing calculus and looking at the derivative of the plot. What is another word for derivative that we might use in this class? Slope. Which in this class we refer to the slope of this graph. What's the slope of this graph called? What do we find when we find the slope of this particular graph? The rate of the reaction. Change in concentration over change in time is the rate. So if we look at how the slope changes over time, that's what we've been talking about the last week, right? If the rate of the reaction changes with concentration, we know something about the order. Aaron?
Sorry, I'm going to ask a bunch of weird questions because I don't follow quite well. So we find the natural log of the concentration, 1 over the natural log of the concentration.
1 over the concentration, not the natural log.
Okay, 1 over the concentration.
Yep.
And then we plot all three of them, and whichever one is linear tells us the reaction.
Yes, and we'll talk about why throughout this class today. So the short answer to Josh's question is calculus. We find that when a reaction proceeds with second order kinetics, which means that the rate of the reaction is dependent on the concentration squared, then that relationship falls out of a graph of concentration versus time. It's not going to be linear, but this graph is going to be. And I have not spent enough time recently brushing up on the calculus, so I couldn't derive it for you, but I'm sure there's plenty of resources we can use if you're really interested in the calculus behind it. All right. So we're going to spend a lot of time kind of deconstructing how to answer that question, what we can do with that, and a lot more than just determining the rate order, because honestly, who cares? And the answer is you do in the end. So we'll get there for that. Two things logistically are supplemental instruction. You guys pick that up. That's activity 58 for the week. It is on integrated rate laws, so if you still don't feel confident today after this, please come to supplemental instruction. I'm trying to figure out ways to make it more beneficial for you, the supplemental instruction, and also reduce my grading load. I can't grade 40 a week, and last week I got almost 40 of these turned into me.
I think so pass-fail would do it, but don't.
Yeah, but the problem is, it seems really valuable. If people do it on their own, there can be some misconceptions that are at the beginning, and they continue through the entire thing. So if people do it on their own and they have a misconception, I feel like it's negligent on my part not to give feedback on that. So I'm trying to figure out the best way to balance that. And if I have to grade them, I do it well. So one suggestion or option that I have is I chose my office hours based on availability, as well as the supplemental instruction times based on availability. And I know everyone can't make all of them, some people can't make any of them. But what if I add to the option of supplemental instruction, if you come and complete it during office hours and work in my office, and you can ping questions off of me, then that would also count as your completion of supplemental instruction. Does that help?
Yes.
So maybe some more people who can't go Thursday night or Saturday midday would also be able to come to Friday 1 to 2:30 or Monday 4 to 5:30. What I might do though is I might change the location because my office only fits about 3 people comfortably. So my second office is in ETAS 125. If you have not been there yet, it is literally this corner of ETAS. So the closest corner of ETAS to where we are right now. There's a big suite in there. It's the STEM Education Center, and I work there half of my time. So there's a lot more space to spread out. There's some big conference tables and that kind of stuff. So let's do that. I'll continue to hold my office hours over there during the same times. If you come and work for an hour on your supplemental instruction and bounce ideas off me, then I'll give you full credit for completing supplemental instruction that week. Does that sound reasonable?
Yes.
I know some people can't make any of those 4 times. I don't have any better options than that, but hopefully it'll be a maximum benefit. All right, any other logistic questions that I need to follow up on? I think that was it. So my goal for you guys today is by the end of today's class, I want you to be able to look at data, a table of data, or look at a set of graphs, and from that be able to determine the rate order of a reaction. And those 3 graphs that we're going to be looking at, also the data we'll be looking at are concentration versus time, natural log of the concentration versus time, and 1 over the concentration versus time. When you have then done that, there are ways to find the rate constant K. You already have some ways of finding the rate constant K with the differentiated rate laws that we did in the packet last week and in class on Monday. Once we have multiple experiments and we know the rate order and the differentiated rate law, we can plug things in and find the rate constant. Now we have some additional ways to find that rate constant. And the reason why we care is because if we take a drug and we know the kinetics of that drug being metabolized, how long until we have a minimum therapeutically relevant concentration in our blood? If there's a radioactive spill, how long until we can go into a specific area? Those are all kinetics types questions. How long until a certain, if we know radioactivity right now, carbon-14 let's say, how long ago did this thing die? And we can back out how long since that was alive, all based on kinetics calculations, okay? So I want you guys all to go back and think about what does 0 order, 1st order, and 2nd order mean. And let's answer this question first, which will lead us into discussion on it. So when we look at a plot of concentration versus time, where are we talking about the rate? And we're going to tie the rate into the rate order in a second. So write down, do I have a spot for this on the worksheet for today?
Yes.
Go ahead and write down your answer for question number 2. Share it with your neighbor. Make sure we're all on the same page.
I should be the one showing myself that.
Okay, so Manu, how would you answer this question? What did you guys? Okay, so if we look at the slope of the concentration versus time graph, we know that that is the rate. Does that change over the course of a reaction? Sometimes. Okay, so that's what I want you thinking about. So the next question then, question number 3, asks, what does it mean to look at the slope, and what do we expect to change about the slope of concentration versus time for 0, 1st, and 2nd order? You guys remember what 0, 1st, and 2nd order means? So let me really quickly just interject so that you guys have a productive conversation. Remember, our differentiated rate laws always look something like this if we have one reactant. The rate order is M. So if it is 0 order, what is the relationship between the rate of the reaction and the concentration of this reactant? there is none. If that's a 0, m is a 0, it means the concentration has no effect on the rate of the reaction. Think about what that means about the slope of that concentration versus time. What if it's a 1? Is the rate influenced by the concentration changes of the reactant? To the first power it is, so it's proportional. If it's a 2, it's an exponential relationship. So we talked before about, okay, initial rate of reaction. Today we're getting rid of initial. We're talking about any time point. You start with a certain amount, what happens to the concentration over time? Concentration goes down over time. What does that mean about the slope? Okay, that's a conversation I want you to have. For 0, first, and second order, what happens to the slope of those graphs as you keep decreasing concentration and reactants get consumed? And just to summarize what we just talked about, here's first, second, and third order. 0, first, and second order. Sorry.
Most of the slopes are all negative, right? Because you're always decreasing concentration. So the question is, how does the slope influence by the mechanism? Does the slope change at all? Zero doesn't change a little bit.
Yeah. How about higher the graph? It would be proportional based on the data. One is like so I'm confused. What is this? Yeah. That's right. So in reality, basically, this one has
There's still something. It's just that the concentration would have no effect on the rate.
okay. I don't know why I'm looking at this from like a physical perspective. We're just talking about concentration, right? No. But this one, the reason why this is in the second order is because it's yeah.
Range is going to be.
That was real loud. So yeah,
All right, I heard some really good conversation when I was out there. Would anyone like to share their group's discussion? When you know that something is 0 order, what are we thinking about? Remember, we're only talking about the plot of concentration versus time. We have a reaction that's 0 order with a reactant. What's happening with the rate of that reaction as the reaction proceeds?
Stays completely the same.
Why?
Because no matter how much of the reactant you have, or the amount of the reactant does not affect the rate. Rate equals K.
Because the rate equals K times whatever your reactant is to the 0 power, which is just 1. So no matter what the concentration is, if we start up here, we get a lower concentration, the rate is the same, rate's the same, rate's the same, rate's the same, rate's the same. So that's what a 0 order concentration versus time plot looks like. What about for a first order reaction? What are we going to expect? Concentration versus time.
Proportional.
What do you mean, Logan?
So as the concentration changes, so will the rate, because it'd be times K times the concentration.
So rate equals K times the concentration raised to the first power. So what is that graph going to look like? Is this appropriate?
It needs to be like a little bump.
So maybe the slope, remember, is the tangent to the line at any point in time. As we get lower and lower in concentration, we have a lower and lower slope, closer to flat. What about second order concentration versus time? I run out of space.
What's that mean?
So there, rate equals K times concentration squared. How does the slope change?
Well,
Leah?
the initial initial rate probably would be as high because you're more reactive. Does that make sense?
So careful, it's not about the amount of reactant, it's about how the slope of that graph relates to the concentration. So, Danielle, what are you thinking? Collins?
Can you decrease in greater and greater amounts as it goes down to smaller and smaller numbers? Or
So careful, you're contrasting using the amount goes down exponentially versus the rate goes down exponentially. So remember, the rate is the slope. So when are we going to have the biggest slope? When we have the most or the least amount of reactant? The most. It's whatever the concentration is squared, so the bigger the concentration, the bigger the rate of that reaction. So you're going to start with a very steep slope, and it's going to kind of have a deeper plunge. First and second order concentration versus time graphs look fairly similar. What's the big difference between them? Is that Ruby? Well, so both of them have the same slope. I saw a lot of people trying to say negative, positive slope. I want you to forget about that completely. Whenever you have a reactant that's being consumed, what is the slope of that graph? Always going to be negative. You're always having less and less and less reactant. We'll talk about in a minute what positive versus negative slope, that's all related to manipulated versions of concentration versus time. But just concentration versus time, you need to just be logical about it. If we're using it up over time, there's going to be less and less there, which is a negative slope. So what's the big difference between first and second order concentration versus time graphs?
The slope is steeper.
Say again?
The slope is steeper for
The slope is typically much steeper, and
at the end it
kind of plateaus a lot more because it's the square of a low concentration. Usually has this kind of plunge to it. But if I were to give you a plot on an exam that just had a little bit of a, a curve, not a straight line, I would expect you to say, well, I need to dig a little bit deeper. You can't just visually look and say, yeah, this looks like first or this looks like second. You need to start looking at some data to make those assumptions, to make those conclusions, and we'll be talking about those utilization of numbers today. All right? So this is what I want you to keep in mind, what 0, first, and second rate order should look like, and then what does that mean about how the concentration changes with time? What trends are we looking for in order to help us kind of speed up in our understanding of this? So let's go ahead and start with looking at this data here. Do you think that this is 0, first, or second order?
just half empty.
can zoom in on your phones. It is also at the bottom of your page. This is question number 4.
What's different about that?
Is there any other data you guys might want?
Go ahead.
What would you like?
On the next page.
Flip over your page.
Situational awareness.
Sometimes it's good to peek.
My screen was frozen, it wasn't doing anything.
First.
All right, we have a 2-to-1 response. Check with someone next to you that you haven't already talked to. Try to determine whether it's first or second order.
Yeah, so this is second. Since this one's linear, the break off.
Expand your capabilities. So I saw a number of people were utilizing their resources and even going one step further and looking at the graphs. To answer this question, I want you to be able to use both graphical data or using just the table itself. If we're using just the table itself and not looking at the graphical representations right below it, how do we determine what the rate order is for this reaction? Love?
I just look for the ones where the change is staying consistent. So, like for example, on the first one, at percent radioactivity, is that radioactivity?
Mm-hmm.
Okay. So from 0 to 5, it's moving around like 20, 23.
Okay, so in a 5-second time change,
Yeah.
we have about 22% decrease.
And then by the last one, it's moving left, like 1.4.
Great. So we know from that right there, it is not what order?
It's not.
0 order. Because if it was 0 order, the change during every 5 seconds would be the same, meaning that no matter how much it had, it would have a consistent decrease in rate of reaction or decrease in concentration during the same time interval. Okay? So then, did you do that for the other ones as well? So if we look for 1 over, is that the same decrease or increase? And this is where the positive slope comes in. We'll get there in a little bit. So this is an increase in 0.0028, if you will. This is almost 300 and some, 0.03 something. So it's much, much bigger change at the bottom. What about the last one?
It's like
0.24 about, and 0.25. Those are pretty close. All right, and we could go check a couple other data points if we wanted. And so what I want you guys realizing from this is that if we have first order, and you have natural log of the concentration versus time, this is going to be a linear relationship between these two. That's with that soft kind of proportional curve. Looking at the derivative of this line and how that changes with time, it is related to a logarithmic relationship.
I just have one quick maybe comment.
Yeah, great.
Question. Prior to even seeing those numbers making any graphs, how often does radioactive decay not follow, or follow any order besides first order.
He's asking me this question.
What do you guys think? Did anyone read that in their book?
It said half-life is
Careful, we're mixing things up there. A consistent half-life is true for radioactivity, and that is true for first order. So radioactivity always follows first order kinetics. Radioactive decay. Nice and easy. So anytime I give you a problem that says percent radioactivity, done, first order. All right, now I know what set of equations I can use. I know what the differentiated rate law is. I know what the integrated rate laws are. We'll talk about those in a minute. All right. The other way to go about this is to plot that data. Which one of those approaches is quicker to determine which is a linear relationship? Does this look a little bit quicker and easier to you guys? So I did give you guys the data plotted on there as well. And I want you to be able to answer the rate order from either a table of data or from the graphical version of the data. Can you see how this is first order here a bit easier? These are a plotting of percent concentration versus time, natural log first, 1 over. So this would be first order if this is linear, which it is. If it was second order, we would see this one being linear. Will we ever see more than one of them be linear? Absolutely not. Mathematically, it doesn't work. All right. So when we're looking at this, if we know that the natural log of the concentration versus time is a linear relationship, then I want us to be able to utilize y equals mx plus b version of that relationship. So let's take 30 seconds, use this equation, and unpack y equals mx plus b. What is which part in here? What does that mean about the graphs that you have? And there's actually a spot on the back, the third page, where I say question number 10. What is a straight line form for each of the rate orders? Remember, this includes initial concentration, final concentration, time, and rate constant. This is the one for first order. So I want you looking at that and unpacking y equals mx plus b. What part is what part of the graph? And you just have an example right above it. Questions of what I'm asking?
Yes.
So what is your y-intercept? What is your slope in that equation? What is your x value? Think about all those things. Look at your plot that you guys just worked with. Trying to figure out how that all fits.
Oh, I don't know. I'm just going based on what you did. I was like, oh, that sounds like that. It's not telling me anything. It's just telling me this is the one that we're working on now. That's the one that we just did
T is always on the x-axis.
All right, can I get a new voice to talk through how this equation relates back to that set of graphs we just looked at? What is y, what is m, what is x, what is b? How to go through all those. New voice, new voice. Tripty?
Okay, so the linear equation is usually y equals mx plus b. So I said that. ln of a is y, and negative k is m. And then ln the initial concentration of b.
Okay. And so then if we unpack what those mean, this is our y-intercept. If you go back to the graphs that you just looked at, what value is your y-intercept?
where it starts at 0.
It's right where it crosses the y-axis. And that's 4.6 something, right, on that natural log value. That's natural log of 100. 4.605 or whatever that number is if you look at the table, right? So if we know, and we're going to be using two different sets of terminology here, and I'm intentionally doing that to make sure you guys are comfortable with it. We have this little 0 and we have t. What does the 0 mean? What does the t mean? So 0 is initial or starting or at time 0. T is at time t. Time t. Time is the t here. You could also see initial and final. You'll see both of those, and I'm going to interchangeably use them on purpose to make sure that you're comfortable not getting stuck in a formula but understanding what it represents. Echo?
So it gives you the concentration that's left over, like after that amount of time, or is it the concentration that's used?
So if you look at the table that you have, the table of data, ln of A is our initial natural log of the initial concentration, 4.605. Pick any time point on that. Give me a time.
5 seconds.
5 seconds. What is natural log of the concentration at that point?
4.3.
That's what you'll have here. So this will be 4.3 something. This will be 4.6 something. Your time will be the 5 seconds. And then your rate constant, negative rate constant is your slope.
Okay. Sorry, so it calculates how much of the concentration is going to, I guess, decompose or consume during that time.
So let's use a little different terminology. It relates the concentration you start with, a concentration at any particular time that you pick, as long as this is the time. So it is the concentration at time t. It is not how much has gone away. If you needed to find that, you would have to find the difference between those, which is a very fair question. Priya?
Okay, so I have a question. Okay, so when it comes to K, and you know like how it's negative, but like in the sense of time is not necessarily negative. So would K always be like, is it going to be positive? Because like time isn't.
Great question. So it's really important to keep in mind what is a reasonable value and what is not. Time is never a negative value of the time you're running a reaction. You're not running a reaction negative 17 seconds. So that means that your slope m is negative k. So if you find the slope of this graph, it's a negative slope because concentration is going away over time. Negative log of concentration over time always goes down. The simplest rule to keep in mind here is the slope always tells you what k is. Can k ever be negative? Can we have a negative rate constant? No. So just take the absolute value of the slope, whether it's natural log of a versus time, whether it's a versus time, or whether it's 1 over. Always look at the slope. That is the value of your rate constant. And then just make sure it's positive. That's where I get really worried. People are like, oh, the slope of the graph is positive, so that means that concentration is increasing. No, that's not how it works. Concentration doesn't go up over time unless you're looking at products, in which case we wouldn't be having a graph like this. All right. There is another version of the first order integrated rate law. That is this one down here. Why might this one be useful? What could we use this version of the same equation? These are the exact same equations, just using the rule of logs to rearrange. Logan?
That'd be useful if you only know the initial or the final.
Okay, well we could also do that here, right? So if we know the initial concentration and how long it's been and the rate constant, we can find what the final concentration is. David?
Maybe to get the line on the same side. Natural log.
The ratio
Clea.
concentrations.
If we want to find the ratio of concentrations, I want to know what percentage is gone, what percentage is still there. And actually, I kind of don't like this version. The version I like better, I think, is actually if you put a negative sign on the right, then it inverts this fraction, and it said what percentage is gone. Or, sorry, what percentage remains. Final concentration over what we started.
Wait. So when you have the reactant at time t.
So if you do multiply both sides by -1, it flips this. So if you're not comfortable with using logs and how you combine, pull apart logs, what negative sign means and does, please spend a little bit of time reviewing that. Find a Khan Academy video that talks about how to manipulate logs. It will be your friend. This semester, one of the hardest mathematical concepts you will use is logarithms. And it will not go away. This is the first time you will see it, and you will see it until the last day of this class. I will provide some resources. Actually, the CHEM1403s. If you go under additional resources, there's a CHEM1403 link. There are links in there under the first part, I think, to logarithms. I will try to find that and post that as well. Just make sure you guys have a direct link to that. So if we want to find the ratio, this is great. If we want to say, well, I know how much I started and ended with, what was the time? This is a nice equation to use. This is easier because it's linear, y equals mx plus b format.
So with that law, you said that's the percentage used, and then the opposite would be the percentage.
Well, so the way this is written right now, this isn't really a percentage, because it's how much we started with over how much we ended with, and that's not a percentage. So if we wanted to do that, it would be negative kt, and you would flip that fraction. That would be the fraction that we have remaining. All right. So let's do a little bit of math with this. All right, this is one of our questions. Question number 5. Get stuck, check with people around you, and then raise your hand. There are 6 of us here to help. So just a quick interruption. What's the big challenge with this problem as I've given it to you right now? We don't know the rate constant, do we? How do we find the rate constant? Okay, we could go and find the slope, but that's kind of a pain. What's another way we can find k? Think about how we found k in the differentiated rate law. How do we find k, the rate constant, in differentiated rate law? Austin?
Doesn't it give us everything that we'll need to find k, like right up there in the table? Because we've got the natural log of radioactivity here, like the concentration, and so we'll just plug in for t time, like we can choose any number that we want for time.
So if we know what the initial, right, ln of A naught is, this is ln of A naught. Be really careful, never plug this in to the initial concentration. This is not the initial concentration, right? I've had a lot of students do that. They take the natural log of 4.605 as the initial ln of initial. You're taking the natural log of a natural log, so don't do that. So we know that at between this time and we can pick any time, right? We could pick the first and the last time. Time is 60 seconds. Ln of A naught, ln of A at time t. We know the time, the only unknown is k. Right? So you guys can solve for your rate constant k. And then if you know the rate constant k, you can apply that to any other scenario. For instance, if you start with this and you end with 3.7%. All right, so raise your hand if you need us to come by. We'll help you move you in the right direction.
I was thinking backwards and I told them no, 47 seconds is when they would have those 7%. Now,
So you said 47 seconds.
why are you doing
45 and 60 seconds. 10.5 and 8.2. So you're saying that this that means that the slope changes proportional. The rate changes proportional concentration. That doesn't mean the concentration is this needs to change proportional. So you need to use this data to figure out what that equation is. Non-generic version of that. This reaction. And then with that non-generic equation, anytime so does that work? Yeah, but it's a different number I have. Yeah, so careful not to use that exact set right there. Natural log. Oh, yes.
Yeah.
Okay, so, and we could choose one, like I said,
That's just what he said. Wait. I was listening.
so when you come to that all then you get
So the ln of A17. That is okay.
because that's what we're getting, what we're looking for. It's like the end.
Oh.
So if we're trying to find frequency opposite that, we know that we take ln as the frequency times that's what means
All right. How do we work this one out? Can I hear from a new voice? How would we work this out? What are the steps that we go through? Kayla? Did you raise your hand?
First, you rearrange the first order equation for K, and I got K equals natural log of A T minus natural log of A 0, not 0, but divided by T.
The whole thing divided by T?
Yes.
I think I agree. Is there one thing missing though?
Negative T.
Yeah, or we have a negative on this side. One or the other. We can't get rid of that negative sign, right? We have to make sure it's accounted for somewhere. So then what do you do with that?
So the natural log of AT is 3.7, and then you plug in the initial natural log, which is 4.605, and you divide that by 60 seconds, because that's the time between.
Careful. I think you're mixing up two different steps. So before we do anything with the 3.7%, we have to figure out what K is. This is a great way to set that up.
My bad. I did 1.609 minus 4.605 divided by 60.
So 1.609, and then you had 4.605, and then you had on the bottom, and that will give us our negative rate constant. What did you find for that value?
0.049.
Does that sound right?
I also think that pretty interesting that the solving state too. Do like the standard class. It is different from that.
Great. How did you solve for it? Okay, so you just found the slope. So your slope on this graph here, which I heard Kalia did as well, is you have your two data points. So you basically pick this data point, find rise over run. It's going to give you a negative 0.049. And then you say that that is the slope of the graph, so K is the positive of that. Either of those ways is totally fine. Now that we know the rate constant, we can do anything we want with comparing time and concentration of that reaction at this temperature. We change the temperature, all bets are off. We have an equation for that. A relationship for that, all right? So then, if we now have our rate constant, how do we actually solve for the time required? Lynn?
You would just take that K, enter it into natural log AT equals natural log of A naught plus the value that you just got for K, and then I did 5 seconds and I just used the last entry on the table. Not 5 seconds. You leave T as your variable that you don't know, and then yeah, and then natural. You wrote it in a different order than me. Sorry, I didn't actually rearrange it.
Fair.
I did 1.308 is what 3.7% is the natural log of that, yeah, and then 1.609 is the natural log of, yeah, one there.
So why did you use that as your value if you're using 60 seconds? And you said how far past 60 seconds is it?
I ended up having to add the t that I got from this to 60.
Great, totally reasonable. It will get you the right answer as well. All right. So I chose to do 0 seconds because then the time I'm going to find is literally the next time point on this.
Yeah. And just solve for t.
And what did you solve? What did your t come out to be?
Well, it ended up being 32.18, but if you add 60 to that, it's 92.18. Is that wrong?
I'm hearing different numbers. Colin, what'd you have?
I got 66 seconds.
Yeah. I got 66.
Logan?
I got, 66.59.
Point what?
59, but it's like 67.
So 66 or 67, I would have to do the calculation to see the actual number. So let's pause and think about what would be a reasonable number. All right? So it's always valid, and then we might find there's something wrong in our calculations. Christina?
It's in minutes, not seconds. Sorry.
Is it minutes or seconds?
It's minutes. If I say 66 seconds is really unreasonable.
So we go back, look at our graph. No, it's great. And it should show up there in a second. It did show up, okay? So if we're looking at time, if we're looking here as it continues down and down, it's kind of hard to tell from the graph. But if we look here, we lost 2%, 1.4%. If we, maybe 1% for the next 5 minutes. So it should be somewhere not too far from here would probably be a reasonable answer, Mo?
You could check by using the inverse of the ln relationship is linear, right? And it's going down at a constant rate. So if you check for 65 by subtracting 0.204 from 1.609, you'll get the time for 65 seconds by doing it by raising it to the power of e.
So I think that there's a lot of really good mathematical ways, and that's a great example of how to do it. So I want you to think about all the different relationships that exist, and if you do that, if you pull out of the equation mindset and just think about how things relate, you're going to do really well at catching errors. Logan, quick.
So when you were writing your stuff on this, you put 609, did you mean 605?
Yes. All right. Let's compare now our differentiated rate law and our integrated rate law. This is our integrated rate law, the one that is, I'm going to circle it in green. That's our first order integrated rate law. What information can we use that equation to help us find? Time to go from a certain concentration to another concentration. What else can we find?
The rate constant.
We can find the rate constant. Great. What else?
You can find the ratio of the concentrations if you subtract.
We can find how much is left, what percentage is left, the ratio of the concentrations. Can we find the ratio of concentrations or time with the differentiated rate law? Is concentration at a particular time, or the change in concentration in this equation at all? It only has the initial concentration, not change in concentration. It doesn't have initial and final concentration. Does this one have time in it? No. We need to use the integrated rate law if we want to see initial and final concentration or time, how those relate to each other. But what does this equation have that the integrated rate law does not? It has the rate. What do both of them share in common?
Okay.
The rate constant. It's what ties these equations together. The same reaction, the same temperature will have the same rate constant. So now that we found the rate constant, we could ask questions about the initial rate if we have a certain concentration, right? So there's a lot of interplay between these two equations, but they allow us to do different things. And what we'll see soon is the Arrhenius equation allows us to say, well, how does temperature influence the rate of the reaction? How does a catalyst influence the rate of reaction? All right, so that's where we're going. So let's look at another set of data here. Try just looking at this data I have up here. Try not looking at the plethora of data. Try not pulling a Josh sneaking out the back. I mean, look at the next page.
See ya!
Ciao. With just this data alone, can you determine what rate order this reaction is?
Can we use this number?
All right, so let me give you the table of data. Is it clear? What if I give you the graphical version of it? Is it clear? Any surprises? Why did I hear a lot of people at first saying this is obviously not zero order?
Because it's going down to
The rate at which the concentration is changing is not the same.
It didn't look the same at first. But the time changes are all different. Don't make assumptions. All right? So this was a student who got a little bit bored and wasn't necessarily doing every 5 seconds and checking the concentration. They were doing it when they felt like it, but they did a good job of recording the concentration at each one of those time points because you can see a very linear relationship. The rate is constant throughout this entire reaction. All right? So for a zero order reaction like this, right, we have our differentiated rate law, which means that the rate is really just equal to K. There's no dependence whatsoever on the concentration. And so the straight line form of that is not too surprisingly. Y is your concentration at whatever time you're looking at. You have your initial concentration as your y-intercept, right? It's what did we start at? That's our initial concentration. That's our y-intercept. And the slope, once again, slope is K. Just make the positive version of it if it's not positive. There is also another version of the integrated rate law, so a lot of times they like to refer to it as this version. So let's answer a question related to this. Go ahead and answer the question, how much reactant do we have left at 30 hours? And no, don't just approximate by looking at it and saying, it's between these two. You can do that first, but then you have to do numeric calculations after. So think about what you're...
Sorry, Ruby, I know I can be like. What do you do first of all?
So I'm guessing you came out. Think about it, write down the equation, so what if I have the equation from the dash? That's what I was trying to think, I was just trying to figure out what equation was I don't know what I mean. I have
K is positive.
I'll see how that makes sense.
Not yet, I'm gonna probably go back and get it. I'll probably go back and get it back. I could have, so I'm not going back to get
All right, let's talk through this one. Can I hear from a new voice how we solved for 30 hours? Avery?
So I isolated K first of the equation.
Okay.
So then I plugged in the 12.3 for that value that we're looking for based off of like the final value.
So you basically utilized this equation,
Yeah.
and you isolated K, and then you did the initial and final on this table?
Yes.
Okay, one thing I want to point out about this is that we've now heard this twice, and it's perfect. How likely, basically what we're doing is we're finding the slope by using the equation. It's the same thing, right? Do you think you're more likely to find an accurate slope if you compare the first and the second point, or the first and the last point?
First and the last.
Why?
Because you're taking over the entire line.
Think about finding the slope here and how a little wobble is going to give you a very big difference versus if you go all the way out here, it's going to average out. So great job, both you and the last person walking us through.
So then I found the K value, which was 2.5 by putting those in. And then I took the equation again and plugged in all the values looking for that A to the A final. So it was negative 2.5 multiplied by 30 plus 100, and then I got 25.
So you found 25. Okay. Do we have one more sig fig? I guess not, because it's two sig figs. All right. And so you found 25 hours. Is that reasonable?
Well, no, it's the concentration that we were looking for. Yeah, it's concentration.
Sorry, my bad. Concentration, 25. That's what I meant. Is it a reasonable number? We go over here, we look at 30 hours, somewhere between these two. So it's going to be a value between these two. So it's in the right ballpark. Samantha?
So I did it like way differently.
How'd you do it?
So because they gave us the 10 hours, I divided the concentration at 10 hours by 75 by 10, and that would give me 1 hour. And then I just multiplied it by 30, and that's how I
Okay, so because you know it's zero order, you know the rate is going to be constant, and you know that the change per hour.
Yeah.
Great. And did you find a similar value?
Yeah, I got 25.
Perfect. Did everyone follow that? If you can find trends, use them. Just make sure it's the right trend for the order that we're using. So we know that because the slope is constant, we know that it's a tenth of this change per hour, so we can multiply that by 25 hours. 30 hours. That's what I meant. Glad you guys know what I mean and not what I say. All right, let's take a look at this graph. What can we say immediately about this last set of data? Just look at that, what's right there. What can we say immediately about it? Not zero order, why? So we have constant time changes, but we have a 28.6, then it's less than 20, less than 10, goes down and down and down. So each of the changes in time are not proportional to changes in concentration. So we know it's first or second order. I'm not going to give you on an exam a 1.5 order. They do exist. You'll see it a little bit in your homework. In our class, 0, first and second order. All right? And then if we took all the data, which of these do we expect to be a linear relationship? It's going to be one of these two, right? Which one of those is a linear relationship? Can anyone spot it? I think you have this as question number 8. You have the data there as well. Is there anywhere where the changes are the same? So all these are a 5-second change, and it's about a 0.004 change between each of those, 1 over concentration. That tells us a second order. We can look at a graphic version of it as well. We can see that 1 over concentration does have a linear relationship. But it's not negative. What's going on? Why is it not pointing down? Your concentration starts out really high, and it goes down over time, right? So 1 over a bigger number is going to be a small number. The smaller your denominator is, the bigger the value is. I really don't care about the slope being positive or negative for this. The slope is k. Let's find the positive version of it. So there's a beautiful integrated rate law as well for this one. 1 over the concentration at time t is equal to the rate constant times time. Notice how the sign is positive because there's a positive slope. I really don't care. Positive version, the absolute value of the slope, plus 1 over the initial concentration.
Great.
Can you guys find k if we have a set of data?
Yes.
Can you figure out what the concentration is at a certain time using the same approach? So the really important thing, the take home that you guys will notice is determine the rate order based on which of those relationships is linear. With that, then look at how you can find the concentration at different times. I'm not letting you guys go. I'm summarizing, so stop backing up. But I want you guys now to answer 2 questions for me.
2 minutes, 2 questions.
Yes. 7 seconds left. All right, this is something I don't think you guys have. What is the rate order? Is it 0 order?
No.
Okay. If we take a look at all the rest of this, is it first or second? You guys want to see the data plotted? What is it? 0 first or second? 0 first or second? Okay. Once again, like you guys, I try to make sure you don't look and assume all time differences are the same. Don't assume that the far left one is concentration versus time. I'm going to move these around, so you need to know what relationship is linear. And then the last thing I want you guys to see, there's a couple examples in there, but this one I think is the most important. All right, let's pull it out. What information do we know? What order is this? First. So now we have a whole bunch of equations. We have the rate is equal to differential rate law. We have integrated rate law. Do we have initial and final concentration? Just initial. Do we have time?
Yes.
So we have the rate constant?
Yep.
Yes.
So if we put all these into action, what do we do here? Logarithms. All right. The other ones are a lot easier to figure out. So I just wanted to show one of these where you have to undo a natural log. So you use E. All right. The supplemental instruction digs into this. Please work on activity 58. Come to my office hours, come to supplemental instruction Thursday night. Saturday is 12 to 1:30 online. Are people still planning to go on Saturday? Raise your hand so we don't show up and no one's there. Saturday. Okay. 4:30 to 6. E-Task 406.
Monday.